Okay, there's a couple more little tiny things that I want to get through in this section. So the first is I want you to go back in your notes to where I told you to write down the additional properties at the start of all this. And I'm going to give you one more property to write in your notebook. And this is a property that I'm never going to test you on. It's just something that is true about Laplace transforms, which is very useful in some applications, but it's like good for you to know, and I want you to have this resource, but I don't expect you to sort of do anything with it in this class. And so it's going to be that L of f of t can be written as 1 over 1 minus e to the minus s capital T, the integral from 0 to t of e to the minus s little t f of t dt for f, a periodic function with period t. So you can decide where on your little table that looks nice. Maybe the same place where you did the original definition of Laplace transforms, because it has an integral in it. Whatever you prefer. Like I said, this will not be tested or anything like that. It's just a useful fact that I want you to have in case you use Laplace transforms in the future. Okay, and then the other thing that I wanted to get through in this video is I want to introduce you to something that we're going to use in the next section. And there's a couple different reasons for this. First of all, so that we can get through more examples in the next section, which I think is a little more challenging than some of this convolution stuff, which is mostly calculus and algebra. But also because this shows up on your project, and I want you to have this like information available if you want to be working on your project during the class when we're discussing convolution and derivative properties. So the thing that we need to prepare for the next section is the definition of delta functions. So the Dirac delta function is denoted by delta of t minus t0. And it's something that's 0 for any t besides t0, and it's infinity at t equal to t0. Another property that this function has is that like when you integrate it, the quote area under the curve is always 1. But what's going to be important for us is the Laplace transform of it. So L of delta t minus t0 is e to the minus s times t0. And I want to kind of like take a little while to build intuition for what the delta function is. Maybe it's shown up in your like physics or engineering classes and you're totally comfortable with this idea. But if you're not, when we start working with this function, it's going to seem like it comes out of nowhere and it's not a very intuitive thing. So I'm just going to draw some pictures and hopefully that'll help us make sense of it. So the delta function is something that takes in input time, and something special happens at t0. So this function is 0 everywhere, and then at t0 it's like this, actually that's not even going to look like it goes off to infinity. It's this jagged thing that goes up to infinity. And nope, wait, I'll do even better than that. I'll make like a little hole. So it goes up to infinity. There's that thing up at infinity right there. And the way you can think about the delta function is it's something where you can think about it as a limit, and probably that's not making it more intuitive for you. So we're going to think about it as squishing another function. So let's imagine that you had something that's more reasonable to think about. You had something that was 0, and then it was like that for a little while, and then it was 0 again. Okay, so there's our t. Kind of clear that I'm sitting there at 0. There's our t. Here's our t0. Here's something that looks kind of like delta, so we'll call it delta approximate. And let's say it's something that had width a, and then its height is, actually has width 2a. So there's some distance a before t0 and after t0 where this little box happened, and then it goes up to height 1 over 2a. And so the like shaded region of this box would be, oh, I'll use a different color. That'll be better. So the integral of delta approx would just be 1. The area under the curve of that box is 1. And then I want you to imagine that we just took this box and we squished it. We pushed it in on both sides. I will use more colors here because that is an option I have. Okay. So squish the box in. Now when I take it like a, say it goes in, now it's a taller box. Same area had to fit under the curve. I squished it, the curve started to go up. Think of it like a bendy cup, and you've squeezed it, and now the liquid goes up and could even overflow from the cup. If I want it to hold the same liquid, if I want it to have the same area under the curve, if the integral stays the same, that means that now my curve is taller. So it goes up like, this is t0 minus a over 2, let's say, t0 minus or plus a over 2. So now its height is like 1 over a. For it to be taller instead of 1 over 2a. And you imagine doing that again. I don't know, get even bigger. It leaves my screen, and then even more gets taller. And then let's head back over here. In the limit, as my rectangle gets thinner and thinner so that it only occurs at a single point, it has infinite height. It gets infinitely thin, and so it's infinitely tall to have that same area under the curve that we imagined before. And so that's how the Dirac delta function works. It's this thing right here that looks like that. And what it represents is when sort of discrete pulses happen to a system. And so we're going to be working with this in the next section. I wanted to introduce you to it if you weren't familiar with it. Don't worry about doing anything with it for class tomorrow. It's just something that you need to know for the lecture video starting next week.